Greetings, folks. So today in this video, I want to talk about how you can use a graph to help kind of visualize the solutions to a trig equation. And the only reason really I'm making this video is because I kind of mentioned this briefly in class, and I saw someone kind of had like a light bulb turned on when I showed them this idea. So hopefully it'll help some of you um, if you were not in that class. This is actually the example that we talked about in class. Solving this equation, sine of 2 theta equals 1/2 for some theta, and we're going to restrict our theta to between 0 and 2 pi, so one full revolution. Um, so I'll briefly just kind of go over the actual solving part. But again, the idea here is that you have some angle, and I don't have my uh, surface on me today, so I can't actually draw things easily, so I'm just going to type things out. There's some angle has a sine value of 1/2. That's what we're basically looking for. I'm going to highlight this some angle part, or maybe I'll bold it, some angle. We know from visualizing our unit circle, or knowing our unit circle, that that angle in the window from 0 to 2 pi anyway, is either, let's see, the angle would be 30 degrees, or pi over 6. So slash pi over 6, or 150 degrees, aka 5 pi over 6. Pi over 6. Now we would add in the to end part every revolution, but because we're restricting our, well, actually, sorry, I'm jumping a little bit ahead. Um, we're gonna need to emphasize that part that any revolution afterward would still work. Um, 2 pi n plus 2 pi n. Again, n is an integer. I'm not gonna type that part. Um, the neat thing about this one is that this angle, or in this problem anyway, that angle is not just theta. That angle today is 2 theta. So the way we're going to write this, let's see, let's copy paste this. So either 2 theta is equal to that, or 2 theta is equal to this guy. Okay, now we can divide everything by 2 here on both of these possible solutions, and we'll get our actual solution set, or at least get closer to it. Theta itself is equal to pi over 12 plus 1 pi n. Just for emphasis, I will write down the 1. Um, or this guy. Oops. So that'll be 1 pi n, 5 pi over 12, and this will just be theta. Okay, so what makes this part now interesting is that because we have altered our equation slightly, we have to still double check to see which possible values of n will keep us within our possible domain of 0 to 2 pi. Because before, remember, we would have thought simply pi over 6 and 5 pi over 6 because those are the only angles in one full revolution that have a sine value of 1/2. However, we're not dealing with those angles anymore, and we're also not revolving every 2 revolutions when we divide everything by 2. We are now starting off at pi over 12 and then going forward only 180 degrees or 1 pi. Um, let me make a little table real quick. Alrighty, so I don't know why this is here. So now I have made a table, plug in all possible, not all possible, but a bunch of n values just to see which of these will fit into this domain that we're interested in. So as you can see, if I plug in 0, well, that's always just the angle that you start with. So of course, pi over 12 and 5 pi over 12 are both between 0 and 2 pi. If I go backwards, obviously when you start here and then go backwards pi, you'll end up at negative pi over 12 or negative 7 pi over 12. So of course these will not are not solutions that we're looking for. Right? So these ones will work. Highlight that. If I plug in 1 and go forward 1 revolution, now I actually will work. Right? Before, if I go at pi over 6 and then go forward 1 revolution, you'll end up at what, 13 pi over 6, which is outside of the window. But now that we've shrunk everything, divided everything by 2 in this step of the equation, of the solution rather, then I will still fit. So 13 pi over 12, 17 pi over 12, both of those are within 0 to 2 pi, and so are also solutions. Once we cross over to a second, um, we tack on a second uh, multiple of pi, now we're outside that window, right? So 2 pi would be 24 pi over 4, excuse me, 2 pi would be 24 pi over 12. So these are outside of that window. So now we have 4 solutions, and this is our solution set. But I do want to take a look at the graphs of this equation so we can actually see why this actually makes sense, where we get now 4 solutions. Okay, doke. So here is my graph. So in red, but also the blue graph is overlaid over it, is the graph of y equals sine of x. Very simple graph. Um, this purple dashed line is the line y equals 1/2. So um, you've seen this, hopefully you've seen this technique before, where you can use a graph to represent a solution. You could always resort to this if you didn't know what the solution was, or you didn't know how to solve an equation, or if you solved an equation and you want to check your work. So if I graph the equation y equals sine of x, I'm really just looking for where the y value is 1/2. And we see here that there are 2 solutions from 0 to 2 pi anyway. Of course, this graph does extend forever, but we only care about the solutions from 0 to 2 pi, so that's why I've only graphed the equation from 0 to 2 pi. Now I made the second graph, y equals b, or sorry, y equals sine of bx. And so b is our horizontal stretch slash compression, also affecting the period of the graph, right? So as I change things, it will change the graph, like we know from the previous chapter. Now check out what happens when I slide it over to 2. Well, hopefully we remember that once I slide this over to 2, this graph will be compressed inward, right? It will get squished, and therefore it will go through its ups and downs twice as fast, right? And so this is not a surprise as to what the graph looks like. But because this has now sped itself up, it goes through not just one full period in 0 to 2 pi, it will go through 2 full periods. Now we can see, oh, hang on, it's actually going to reach that height of 1/2, not just twice anymore, but it will go once, or sorry, twice in the first period, and then twice again in the second period. And that's why this has now 4 solutions, whereas before it only had 2. Okay, so hopefully this helps kind of visualize and explain why this suddenly has different numbers of solutions based on what's happening in the argument inside the trig function you're dealing with. There are also other transformations, of course, right? So if I shifted this thing in addition to stretching it or compressing it, that will also change your solutions. So for example, if I tacked on or changed this to, you know, x minus pi over 3 maybe, right? It will still have 4 solutions, but it'll just be shifted over. Okay, so hopefully this video was enlightening, at least to some degree, and catch you in the next one.